Recording is rolling. It is Thursday, May 8th. We're going to finish this final exam review. So, part three on Kahoot, of course. You guys have your study guides out. You guys have the same questions, follow along here. You guys remember our exam format? Going to be 50 of those conceptual questions, followed by 10 algebra-based questions. I'll give you guys the equations for those. All right, so with all of that, flip over to Kahoot. The fundamental force underlying all chemical reactions. Electrical. Okay. Uh, actually, they were talking about recently, right? Because like what explains all the chemistry and layout of the periodic table and chemical reactions it has to do with the arrangement of the valence electrons. So it's something about electromagnetism. Now, the poster you guys saw flash up there, which will show up also near the end of this when we get to the quantum section proper, was that there are four fundamental forces in nature. Okay? There's gravity, which actually, if you talk to Einstein, you might even argue that's sort of an artifact of curvature space-time. So, but whether you consider that or not, there's electromagnetism, which covers almost everything else. So that's electricity, magnetism, obviously, but also chemical reactions, contact forces, friction. Right, that's all electromagnetism. And then there's a couple of forces that we don't talk about very much in this class, but when we get to quantum, which are two nuclear forces. So one's called the strong nuclear force, right? Binds all the protons and neutrons together in the nucleus. And there's a weak nuclear force that is related to radioactivity. All right. So you guys know all of chemistry is explained by electromagnetism. You guys got that? All right. Got points on the board. 6469639. To be safe in the unlikely case of a lightning strike, it's best to be inside a building framed with. What's that kid in right there? Yeah, there you go. How about some kind of metal frame, some kind of conductive material, so that the current has a path of least resistance down to the ground that's not through you. Ooh, is that called a Faraday frame? Faraday frame? Yeah. Ooh, we sitting in Florida, lightning capital of the world. Suppose there's a lightning storm outside. Where would you be safer? In the field outside or inside this building? Let's go inside this building. And do you think this building is framed with metal? So if lightning strikes it, just carries that current all the way to the ground. There you go. At Luciana, Olivia, Miko, Elise, Tommy Two-Tone. Two charges separated by 1 meter exert a 20 Newton force on each other. So some kind of electrostatic force. If the distance is doubled, the new force will be basically force is proportional to 1 over the distance squared. So if you double the distance, ooh, no winners, no winners. All right, so here, take that. Here, bring this over here. Give you guys an example. Okay. So you guys remember universal gravitation? The gravitational force say between the Earth and the Moon was universal gravity constant, mass of the Earth, mass of the Moon, divided by the separation distance squared. Okay. Now, when you get so that was gravitational force. When you get to electrostatic force, so the force between two charged particles, it's a really similar looking setup. So we got electrostatic constant times the charge of one particle times the charge of the other particle divided by the separation distance squared. This is what you guys just saw, right? Right. Of course, we're talking about electrostatic, not gravity, but I want you guys to see that those two take the same form. Okay. Now, here, let's come up with some numbers. Say, say you have some distance between two charged particles. What if this has a charge of let's say 4 units, and this is 5 units. I don't know, whatever those are. And let's say K, I'll just call it 1 for whatever these units are. Okay. So could the original force be 4 times 5, and let's call it distance equal to like 1 meter. Right? I'll just call it 1 unit. 1 unit squared. Could that be like 20 units of force? Let's call it like newtons. It's okay. I'll call K equal to 1 just to round it up. Okay, you guys get that? Okay. Now, I'll say the new force could be, guys, if you very simply double this distance, everything in the numerator stays the same. So 4 times 5 is still 20. But guys, what's 2 squared? Is that 4? And what is 20 divided by 4? 5. Right, and let's call it news to make it a force. Right? That was the exact answer. Right? But more importantly, like, what do I want you guys to get from this class is to be able to see the relationships within these equations. So an inverse square relationship between force and distance, there's an inverse square relationship. So when you guys get this final exam in a few days, the numbers might be different. Right? It might not be 20 newtons. It might be some other number. Right? But you can still navigate an inverse square relationship between force and distance. So if you double the distance, double squared is always 4, and it's 1 over that. So it's always a quarter of the force. A quarter of 20 is 5. Right? Or, guys, what if you get some like 3 times the separation distance? Guys, 3 times the distance is how many times the force? 1 over 9. Yeah, 1/9. And then so whatever the original force is, you just divide by 9. If it's 3 times the distance. Okay, can you guys navigate inverse square relationship? Pretty good? All right. Good deal. Yeah, Luciana, Olivia, Miko, Elise, Tommy Two-Tone. Electrical resistance in a wire depends on the wires. That's where we're doing that Play-Doh lab. Yeah, there you go, all the above. Right. So that's what that poster said, or all those variables were factors in that equation. Oh, you guys remember sending an electric current through a cylinder of Play-Doh? And you had to measure what's the length of the Play-Doh. You had to measure the diameter so you could calculate the cross-sectional area. That's something to do with thickness, right? You were trying to figure out what's the resistivity, and you measured the current and the voltage to calculate the resistance. There, so all those are connected together. Okay, all the above. Right, you guys good with current through a wire? Compared to thin wires, the electrical resistance in thick wires, it's the same formula. If you increase this cross-sectional area, what happens to the resistance? Yeah, be less, right? Is that true? Right? If you make that cross-sectional area big, the resistance gets small. Right? Think it's easier to push electricity through a thick wire than a thin wire, which is what that says too, right? Well, suppose you're driving out on the road. You got a little 2-lane road and you got a big 10-lane superhighway. Same number of cars, just keep it real simple. Right? Is it easier to drive on the road with more lanes on it? Yeah, right. A little analogy there. What do you think of this? I got Luciana, Alexander, Elise, Miko, Tommy Two-Tone. Primary reason a bird can perch harmlessly on bare high voltage wires, but 100,000 volts doesn't get fried. Why? Yeah, potential difference. If there's no potential difference, if his right foot's on 100,000 volts and his left foot's also on 100,000 volts, there's no potential difference. Now, we're about to break open Ohm's law pretty soon. You guys know current is voltage over resistance. Guys, when I say voltage, really that's a potential difference, right? Guys, if you have a 9-volt battery, those little box silicon 9-volt batteries, there's a potential difference between the two leads of 9 volts. You can maybe call one at 9 volts and the other at 0. And then if you can create a circuit that connects those two, okay, you need a potential difference. All right, you guys go with the bird? All right, I got Miko, Tommy Two-Tone, Luciana, Elise, Alexander. 8-volt battery connected to a resistor, 2 amps of current flows. What's the resistance? Help you guys out here. So Ohm's law, where the V goes, put 8 volts. Where the I goes, that's current in amps. Put 2 amps. Guys, 8 divided by what is equal to 2? Yeah, 4 ohms, right? So 8 volts potential difference acting on 4 ohms results in 2 amps of current that flows. All right, you guys good with Ohm's law? I think the next one's also Ohm's law. Let's see if that's true. All right, we got Ziriana, Miko, Luciana, Elise, Tommy Two-Tone. Back to the top. When connected to 110 volts power supply, how much current is a light bulb with resistance of 220 ohms. Let's try this. Help you guys out here. 110 volts on 220 ohms. Well, what's 110 on 220? Yeah, half an amp. Okay. Now, most importantly for the notes you're taking right now on your study guide, you just have Ohm's law. You guys can navigate Ohm's law. Because on your exam, of course, the numbers might change, but it'll still be an Ohm's law question. Okay, so everybody go with Ohm's law. Light bulb plugged into 120 volts has 0.7 amps of current in it. Oh, what's the power rating? Ooh, power. Here, use this first one right here. P equals IV. Power is current times voltage. Try that out. Yeah, 84 watts. There you go. Okay. So power is current times voltage. Current 0.7 amps times voltage 120 volts gives you 84 watts. Everybody good with it's called Joule's law, right? There were a few different forms of that. Right? So again, some variables. Right? Anything to do with power probably involves one of those, like power Joule's law. Peyton, Ariana, Miko, Alexander, Elise. A closed circuit is a circuit in which charge can flow, right? Because you need, if you want to connect a circuit to, say, turn a light bulb on, you have to have a closed circuit. If you have a on-off switch and you hit the off switch, that opens the circuit, and then there's no path from the cathode to the anode, and no electricity flows. If you close the circuit that's hitting the on switch, now there is a complete path, and the charge can flow. Right, you guys go with, you need a closed circuit, right? You need a closed circuit to have electricity flow. Peyton, Zach, Pico, Alexander, Elise. As more lamps are put into a series circuit, the overall current decreases. Right? Now, maybe this is actually like a two-part question because there's a middle question that could be helpful. Guys, as you put more and more lamps in a series circuit, what happens to the resistance? Yeah, increase. So the resistance increases, and if you hop over to Ohm's law, with an increasing resistance, then the current would also decrease, right? Which leads to that answer right there. All right, so you guys go with series circuit. All right. As more lamps are put into a parallel circuit, the overall current increases, right? Maybe a couple ways to think that. You guys saw the picture, they were like rungs of a ladder, right? You guys remember when either you did this during your lab with the Christmas lights or when Paul Hewitt did with the car battery? Every time you put on a new lamp in parallel, like rungs of a ladder, the other bulbs just maintain their brightness. And so the new bulb would get the full voltage across it. So it was a new path for more current. Yeah, so right. And a different way to think of it is that because what happens to the resistance of the overall circuit as you add more in parallel? The resistance does what? Actually decreases. Yeah. And then hop over to Ohm's law. Therefore, the current could increase. So same answer from a different way to get there. A couple ways to think about that. Yeah, Elise, Miko, Peyton, Alexander, Zach. When one bulb in a series circuit burns out, burn one of those bulbs out. What happens to the other bulbs? Yeah. None of the other bulbs light at all. Because wouldn't that open the circuit Right, and there's no path for the electricity to flow through. Right? So you burn one bulb. That one bulb burns out. That opens the circuit. Now there's no complete path from the cathode to the anode. All right. I got Nico, Peyton, Alexander, Elise, Zach. When one bulb in a parallel circuit burns out, the other bulbs. This one. To the other guys. Yeah, burn the same as before. Burn the same as before. Oh, here, let's take a look at that. Okay, here's before. Okay, so first let's go through that backwards. What if we're constructing a circuit from scratch? You guys remember like Paul Hewitt had a 12-volt car battery? Okay, and it sits on one bulb. Now, does this one bulb have 12 volts across it for a 12-volt battery? Yeah, and then whatever resistance, Ohm's law, get some current flowing. Okay, now if you wire another bulb in parallel, like rungs of a ladder, does this bulb also have the full 12 volts across it? It does. So when you connect it, does the original bulb maintain its brightness? Yeah, just as bright as it was before. Okay. Now, from the battery's point of view, did you effectively just double the total amount of current leaving the battery? Because not only does it supply this bulb, but now it also supplies this one. Okay. Now throw on a third one, also parallel. Now this one bright, now they're all equally bright. They're all super bright. Okay. Okay. So working backwards, if that one burns out, isn't there still a full 12 volts across that one and also that one? So the current flows just run through those. Yeah, so the current still flows. There's still a path for the electricity. All right, so everybody go with this. All right, Alexander, Ziriana, Miko, Elise, Zach. A short circuit. Yeah, the positive connected directly to the negative. You could also say where there's negligible resistance in the circuit, or you connect the positive to negative just by a wire. Right, a wire has a tiny, tiny, tiny amount of resistance, so approximately zero. Okay. Now, where have you guys seen a short circuit? Okay, so I'll show you guys a couple examples here. One is there's a page I gave you guys. You guys remember that circuits page? Circuits page. I think it was like number 9 and 10 on the circuits page. It looked like this. So there was some voltage source. I think it was 5 volts, and I threw in some resistors, something like this, and then only one of them was like this. It had a wire going right down the middle. You guys remember that? Okay. Now, guys, from the point of view of the electric current flowing around, let's do like the flow of positive current, just convention, whatever. Okay. Has to go through this resistor, hits this junction, and then, well, go to the left. I see a bunch of resistance that way, but isn't there basically zero resistance along this wire? So this wire has a name, starts with an SH. It's called a what? Short. Aha, short. Doesn't 100% of the current go along the short? That just shorts out these two. These aren't even part of the circuit, are they? Isn't this your entire circuit right here? That's it? That's the entire circuit? Okay. Oh, now another place you guys saw a short, sort of. You guys remember how those box silica 9-volt batteries? About 9 volts. That positive, negative terminal. Okay. Oh, guys, what would happen if you take a paper clip and you connect the positive directly to the negative? So something about like that. Okay. Does the paper clip get really, really hot? Yeah. Could you start a campfire with that if you had to? Yeah. But otherwise, other than maybe something like that, would that be an ideal situation? Do you normally want to do that? No, because that would burn that would drain the battery really fast. Otherwise, it'd be pointless. Yeah. So, short circuits. Come on here. All right, you guys go with shorts. We've got Nico, Peyton, Alexander, Zach, Elise. Total resistance of 10 ohms and 7 ohms in series. At 17. Because in series, you just add the resistors together. Okay. Now, of course, on your guys' exam, the numbers might be different. But you guys know the rule, you just add them together for series, right? Just add them together. All right, so everybody knows how to find resistance in series. Total resistance of 6 ohms and 12 ohms in parallel. Ooh, parallel. Could that be product over sum? Well, guys, what's 6 times 12? Is that 72? What's 6 plus 12? Is that 18? What's 72 divided by 18? Product over sum. Yeah, 4 ohms. Right. So 2 resistors in parallel. You can always do product over sum. That'll work. Right. Guys, what if you have 50 resistors in parallel? Do you think it might be better to use the reciprocal method with the fractions? So 1 over plus 1 over plus 1 over, 1 over Alan plus 1 over Bob plus 1 over Chad. So, how about this? Let's switch stories. What if it took you 6 hours to paint a fence, and it takes your friend 12 hours, but you're going to team up and make a 2-person team? How long does it take you two together? Think about 4 hours to paint the fence, right? Same answer, same answer, same math, right? All right, everybody good? You good? I got Zariana, Peyton, Zach, Alexander, Elise. If you break a bar magnet in half, so all magnets have dipole, have a north and a south. Right? There's no unipolar magnet. Right? Magnets are going to have a north pole and a south pole. North pole, south pole. So you guys know magnets have 2 poles. Put that in your notes. All right. A device consisting of a coil that's mechanically rotated in a stationary magnetic field. Right, so we're taking mechanical energy, trying to generate electricity. What device would that be? Yeah, generator. Right, generator. Right. So most power plants involve boiling water to turn a turbine, and that would force a wire past a magnet, and that will generate electricity. That's taking mechanical energy and moving that energy onto the electric grid. So by forcing a wire past a magnet, that's a generator. Okay. You can also, how about a wind turbine? Right, same idea, force a wire past a magnet with wind. Or how about hydroelectric dam? Right, same idea. You can force a wire past a magnet. You're generating electricity. I got Zach, Luciana, Alexander, Peyton, Elise. A device that transforms electrical energy back to mechanical energy. Well, that's called a motor. Yeah, a motor. Right. Guys, could a motor and a generator internally look the same? They both got a wire. They both got a magnet. Yeah, but they're doing exact opposite processes. Actually, you could use one as the other depending on which way you're routing the energy. Right. So a motor takes electrical energy through a wire, runs that nearby a magnet, and that generates a physical force. So now you get mechanical energy. Now you can run a ceiling fan or anything kind of mechanical motion. Right? Guys, some of you guys picked transformer. Do you guys remember what a transformer is? So if you have a couple of inductors, you can transform the voltage level. Say if you want to go from 100,000 volts down to 240 volts, right? You can jump up the voltage, you can jump down the voltage. You guys remember inductive coupling? Inductive coupling? That's a transformer. All right, so you guys go generator, motor. Good. Most commercial generators are driven by got a boiler in it. Steam. Okay. So how do you get energy from coal? How do you get energy from natural gas? How do you get energy from nuclear? And the answer is all the same. You boil water, and the resulting steam turns a turbine, which forces a wire past a magnet that generates electricity. That's how you get that energy, any of those forms of energy, onto the electric grid. It goes through steam. Yeah, it's called the Rankine cycle, right? Rankine cycle. Right. Now, the exceptions to that would be wind, hydroelectric, and solar would not have to go through steam, but all those others. Ooh, we're on to relativity. Light is different from other objects. No matter how fast the source of light, light always. Remember that Michelson-Morley experiment? They found that light always has the same. Yeah, speed. There you go. Same speed. Okay. So Michelson-Morley, whether they're bouncing the light east and west or north and south, it made no difference. Spring to summer to autumn didn't make day to night didn't make a difference, right? And you can extrapolate that and say, well, actually, some questions coming up, right? If you're say in a moving vehicle and you measure the speed of light, right? It's the same no matter what, no matter your frame of reference. See if that's the next question. Actually, well, it's one of these coming up. Einstein reasoned that, see, all motion is relative. A spaceship cannot measure its speed relative to empty space. A spaceship can only measure its speed relative to other objects. All the above. What does Einstein relativity mean? Yeah, all those are implicit in Einstein theory of relativity. Okay. So if you go back before Einstein, so it's like the Newtonian physics era, you say, well, you might imagine that there's like some post in the universe you could measure everything with respect to, but Einstein says, not so fast. All right, Zach, Luciana, Alexander, Peyton, Elise. A spaceship moves away from a space station at half the speed of light. If a person in the space station flashes a light beacon, people in the ship will see that light traveling toward them at a speed of. Yeah, speed of light. Okay, so speed of light is the same regardless of your frame of reference, which is strange because if you asked Isaac Newton probably would have answered the red one. Said like what? So here, just to really hammer this home. You guys remember? Suppose I got a truck going on right here. You guys see this truck? You guys see this guy with the baseball? And then there's a guy over here on the grassy knoll with a radar gun. Okay? And if this guy throws the baseball with some speed, B for baseball, but the truck is also in motion, BT for B truck. And you say, how fast is the baseball going? Well, if it depends on which guy you ask. Because if you ask the guy in the truck, the speed of the baseball is just however fast he threw it. If you ask the guy on the grassy knoll, then you have to also add the velocity of the truck. So they give different answers. But what if I ask the question, what's the speed of the light in these headbeams? This truck just turn on its headbeams. And if they both bring out the Fizeau cogwheel and measure the speed of light, guys, do they get exactly down to the millimeter per second, the exact same for the speed of light, even if the truck is in motion? Yes, they do. Yes, they do. Okay. And Einstein was looking at experiments like that, including Michelson-Morley and some other ones, saying, the only reason, or the only way to square that circle, right, is for there to be time dilations. You have to remember time dilations, right? And it's coming up pretty soon here. Oh, here we go. Twin paradox. Earth twin views rocket twin's clock as running what? Yeah, slow. Right. Remember, Earth Twin sees his own clock as beating 1 second per second. If you're on the ship with Rocket Twin, you see your own clock is also beating 1 second per second. The conundrum is when they break out telescopes and they look at each other's clocks. Okay. Now, help you guys out a little bit here. On the study guide, this question is worded a little bit different. This came up earlier. So it's the one that says Suppose we observe light bouncing back and forth between two vertical clock mirrors in a spaceship whizzing past us at a very high speed, which is what the picture on the poster was. Well, it was a train, but same idea. Compared to what the person in the spaceship sees, that would be rocket twin. When we, that'd be Earth twin, see the spaceship clock is running what? So you guys see it's the same question though, right? Right. Just that's a lot of text, and Kahoot only allows so much before I have to say C question. So that's up there. Okay. It goes like this. So Earth twins time equals rocket twins time divided by this Lorentz factor. So square root of 1 minus v squared on c squared, where v is the speed of the rocket and c is the speed of light. Okay. Hey guys, this Lorentz factor in the square root is always bounded between 0 and 1 for a relative speed, between 0 and 1. Because when you take rocket twins time, so suppose rocket twins been flying around for a year. It's been a year. And you divide by a decimal between 0 and 1. Does that make Earth twins time less than 1 year or more than 1 year? Let's try it out. What is 1 year divided by 0.5? Ooh, that'd be 2 years. Ooh, let's try a different one. What's 1 year divided by 0.05? So as he gets the ship going even faster. Ooh, 20 years. So rocket twin's been flying around for a year. He comes back to Earth. Earth twin says, "It's been 20 years, brother." It's 20 years. So it's more time for Earth. So then if Earth twin is always looking at rocket twin's clock, it looks like it's going to tick like real slow. And that's the answer to the question you guys just answered. Okay. Right, guys good? Yeah, Zach, Luciana, Alexander, Peyton, Elise. To calculate how much rest energy an object has, you multiply E equals mc squared. Yeah, mass times speed of light squared. So isn't that the energy of nuclear reactions? When you run a nuclear reaction, it's like, oh, I'm missing some mass. Where'd the mass go? Well, converted to energy. How much energy? Mc squared. E equals mc squared. Energy is mass times the speed of light squared. Nuclear energy. You guys good on nuclear energy? If Einstein's equations for special relativity are valid, they must say reduce to Newton's equations when the speed is small, agree with correct results from Newton's equations, give correct answers for speeds much less than the speed of light, all the above. There's Einstein's equations right there, some of them. Yeah, all this will be true. That's called, do you guys remember the name for that principle? It starts with the C. It's called the correspondence principle. Okay. Which goes like this. If you come up with a new theory for how something works, and it's going to replace an old theory, just like Einstein physics replaced Newtonian physics, then your new theory has to do two things. One is that it has to cover the basis of what the old theory was good at predicting anyway. Like Newtonian physics was good for hundreds of years for a reason, right? And Einstein's equations reduced to Newton's equations at slow speeds. Okay. But your new theory also has to be able to explain that phenomenon that the old theory couldn't. And Einstein physics can do that too. Right? Can explain like GPS and the orbit of Mercury and things like that. And Zach, Luciana, Alexander, Peyton, Elise. Ooh. Grace. Oh, quantum time. Light behaves as a what? Yeah. You guys remember wave particle duality? So remember how this is we're up to the journals that you guys are partway through keeping, right? Okay. So for hundreds of years or for a long time, it was understood that light has wave properties, right? Cut a couple slits in a card, shine light through, interference pattern, hence light has wave properties. But then there's the photoelectric effect, late 19th century. Got Heinrich Hertz, Albert Einstein looking at the photoelectric effect, saying, hey, I know we could explain this as if beyond the threshold frequency, if you say double the frequency, you double the energy you could collect. That would only work if light also has particle-like properties. And the particles of light, Einstein was calling photons. You guys remember all that? Okay, so wave particle duality. Wave particle duality. A photocell can be activated with a blue light, but not a red light, because blue light has, here's red, here's blue. Blue light has a Oh, look at you guys. Yeah, higher frequency. Higher frequency. So photoelectric effect. Yeah, Zach, Luciana, Alexander, Peyton, Elise. The wavelength of a particle, any particle, is called the de Broglie wavelength. There you go, de Broglie wavelength. Okay. Remember, so Einstein established this wave particle dual nature of light, and then de Broglie says, I wonder if that could apply to other things. Hey, maybe like electrons. I might uh, explain chemical reactions we're about to get to. Actually, aren't we getting close to that very first question in this Kahoot? So all chemical reactions are fundamentally electrical in nature, right? Because we're talking about electrons just orbiting atoms, different configurations for different atoms. All right. I got Zach, Luciana, Peyton, Alexander, Elise. The discrete orbits of electrons are best understood by considering the electrons. Wave properties. Yeah, wave properties I'm looking for. Okay. If you think of electrons as wave, think that de Broglie wavelength, right? If electrons have a wave property, if you need to complete an orbit with a complete number of wavelengths, that would limit the locations that you could orbit an atom. Okay. So gives you energy levels, discrete orbits. Zach, Luciana, Peyton, Elise, Alexander. Nuclear fission. A nucleus divides spontaneously with no apparent reason. Electrical forces inside a nucleus overpower the nuclear forces. What sounds more right? Yeah, there you go. Okay. So the poster that was up there showed the four fundamental forces of nature. Now we haven't quite got to that part in the quantum journal yet, but you guys seen a little bit of fusion and fission. Okay. So what's holding the nucleus together is the nuclear forces, a strong nuclear force. Okay. But some nuclei are more or less stable than others. Like I know uranium 235, U-235 is not super stable. It's radioactive. So if you bombard it with neutrons, you can overpower that nuclear force and force fission to happen. Yeah. So the nuclear forces would be overpowered by electrical forces. There you go. Yeah, Zach, Luciana, Peyton, Alexander, Elise. Nuclear fusion releases energy when yeah, very light nuclei fused together. Okay. Typically, what hydrogen to make helium, okay. And so people are working on trying to build a fusion power plant. We're not quite there yet. Right now, guys, all our nuclear power plants right now are what kind of power plants? Fusion or fission? Yeah, fission. Right. So we're breaking apart like mostly uranium, maybe some plutonium. Right. Getting energy that way. Right. But hopefully within our lifetimes, you guys are going to see fusion power plants, and they might take different isotopes of hydrogens. They call it deuterium and tritium. They got extra neutrons. Right. Guys, can you extract energy out of fusion pretty much all the way up to iron, right? And then iron is like the tipping point, right? It switches over to fission to get energy, to extract energy. All right. Everybody doing all right so far? The primary fuel for fusion yeah, let's definitely go with hydrogen. Okay. Oh, isn't that also the nuclear reaction happening in the sun? Right? Isn't that where the vast majority of sunlight comes from? Hydrogen fusing to helium. Okay. So hydrogen fuses to helium. Now the tricky thing is if you start with helium, because some of you guys picked helium, is that actually it absorbs energy to turn into lithium, so that's not very helpful. But then, okay. And uranium and plutonium, those are you can get extract energy by fission, but not fusion. Okay. Is everybody good with raising hydrogen for fusion? Got Zach, Luciana, Peyton, Alexander, Elise. Oh, I think this is for the win. Are you guys ready for the win? For the win! For the win! A nuclear process that has relatively few radioactive byproducts. We're going fusion. Fusion. Okay. Guys, didn't you guys just tell me that all our modern day power plants are some version of fission? Right? And guys, don't nuclear plants today, like fission plants, have lots of radioactive waste? And we have to manage that somehow because it'll be radioactive for thousands and thousands of years. So we got to figure out a place to store it that's not going to contaminate the wider environment and it's not going to hurt people like thousands of years into the future. Right? How do you do that? Right. Okay. But fusion, guys, when we crack this puzzle, which can't hopefully within our lifetimes, we'll see. Time will tell. We're just taking isotopes of hydrogen, fuse that helium, extracting almost 1,000 times the energy. That's another advantage of fusion too. Get almost 1,000 times the energy out of that process. Okay? But yeah, hardly any radioactive byproducts out of that. So it's a lot cleaner, a lot safer, a lot more energy. All right, let's see who won. Who won the Kahoot? With the bronze, Peyton. With the silver, Alexander. And the gold, Elise. All right, nice job, guys.